Can everybody hear me okay? Yep, fantastic. Keeping an eye on the universe. As you can see from the subtitle, what I'm going to be talking about is looking at a few telescopes and asking what do they tell us about how the universe works. It's not going to be too technical. There's a little bit of technology in there. There's a little bit of science. If you don't like that, just go to sleep for a little while and enjoy the nice photographs, the nice pictures, the nice images. So, telescopes have been with us for quite a while. Since the time of Galileo, 400 years or so, we've been using telescopes. And of course, this is what people think about. When you say a telescope, they assume it's the Lord Nelson type, Galileo type telescope, a long, thin object, probably got lenses at one end that focus the light and show you what's going on in the universe. But of course, that is very old technology now. The technology of telescopes has developed a huge amount in 400 years, and it didn't take long before different styles of telescopes led to professional astronomers making telescopes essentially as large as possible. What's the advantage of making a telescope larger? Well, it's twofold. If you've got a larger lens, or these days it tends to be a mirror collecting the light rather than a lens collecting the light, if you have a large mirror, you can look at fainter objects because you're collecting more light. And one of the laws of physics is if you've got a larger mirror, you can see finer detail. We won't worry about how that comes about, but that's one of the advantages of going for larger telescopes. So you get fainter objects, which quite often means more distant objects, and you can see more detail. So there has been a long, centuries-long push for making telescopes larger and larger and larger. And these days, not content with the idea of using a telescope and looking through the Earth's atmosphere to see the wonders of the universe, perhaps you're already aware of the fact that we have a number of different space telescopes which get above the Earth's atmosphere, so you don't have the inconvenience of a blurry, turbulent Earth's atmosphere. You can see through all of that and see clarity in the distance. So we have things like the Hubble Space Telescope, the iconic telescope that's been around now for more than 30 years, and more recently, the James Webb Space Telescope, which was launched just a few years ago and went up on Christmas Day 2021. So that has added to the complement of telescopes that are scattered around the world. Having a few in space gives us an advantage, gives us a different eye on the universe, if you like. But there are even more exciting developments coming along, because for the last few years, people have been designing and building a new generation of telescopes, and one of them is the European Extremely Large Telescope. You can see people are absolutely awful at naming these things. They've had the Very Large Telescope, and now they've got the Extremely Large Telescope. They really ought to come up with better acronyms than that. But I'm sure you're having difficulty getting the scale here, but right at the front, there's a couple of people. So you can see, when they say extremely large, they do at least mean extremely large. So yes, from the days of Galileo, when telescopes were measured by the size of the so-called object glass, the lens at the front, measured in centimeters, now we're talking about telescopes usually made with mirrors, because it's easier to make mirrors than it is to make lenses. Now we're talking not centimeters, we're talking how many meters across are these various telescope mirrors. And it's difficult to gauge just how much things have changed, but if we map out how they've changed in the last few decades, this is not going all the way back to Galileo, this is just recent stuff. And you might have difficulty reading all of the legend, but basically in the top left, this is all various telescopes, lenses and mirrors to scale, where the top left is a lens that's 1 meter in diameter. That's the largest lens that's ever been made for a telescope, 1 meter in diameter. Since then, back in the 1900s, they've been making mirrors because they're easier to make large. But just look at the relative size of all of these mirrors. Some of them are circular and made of glass, and some of them, you notice, are this honeycomb hexagonal structure. That's simply because it's easier to make a large mirror out of lots of smaller mirrors. It's simply easier to manufacture that way. It's just as demanding in terms of the precision you need to make the mirrors, but it's just easier to manufacture. The largest telescope in the world at the moment is the Gran Telescopio Canarias, which is the one in yellow at the top. That is of order 10 meters in diameter. Of course, if it's a hexagon, it's not really a diameter, but you know what I mean. It's about 10 meters across, made of a number of different hexagonal segments, and that's sitting on the top of La Palma in the Canary Islands. If you compare that with the size of space telescopes, here we have in the bottom left corner a number of different space telescopes, some you might not have heard of, but if we concentrate on the ones you have heard of, the Hubble Space Telescope, only 2.5 meters in diameter, and the James Webb Space Telescope of order 6 or 7 meters in diameter. You notice they're relatively small compared to some of these very large mirrors that are made for telescopes on the ground. That is simply the obvious statement that it is difficult to get a telescope into space. You have to put it on the top of a rocket and get it up there. Therefore, you don't try and put enormous telescopes in space. You make do with somewhat smaller ones, but you still get the advantage of being above the Earth's atmosphere and so being able to see objects clearly. And again, because it's difficult to gauge the scale, I can say that that is 10 meters across, the yellow one at the top there. But it's difficult to gauge scale, so there's a human to the same scale. And if a human isn't good enough to give you the scale of these mirrors, there's a basketball court and there's a tennis court to the same scale. So these things, some of these mirrors are literally the size of this lecture theatre, literally. Not just a few centimeters across, not just a few meters across, but many meters across to the point where the entire thing would essentially fill this theatre. We'll come back to some of these larger ones in due course. But very few people can not be familiar with the iconic Hubble Space Telescope. Even if you're not an amateur astronomer, let alone a professional astronomer, people would still recognize this as a scientific instrument. The fact that it's been producing interesting images since 1990 or thereabouts when it was launched, it had a little problem with the optics that needed fixing, but for 30 years it's been producing some very interesting images, a few of which I'm going to show you now. One of the most iconic feats of the Hubble Space Telescope was looking into a patch of sky where it was assumed there's probably nothing there, but let's look anyway. Let's take a really long exposure to see anything really faint in this patch of sky where we don't think there are any stars or anything else going on. They exposed for about 1 million seconds, so they exposed this particular image for about 10 days, and they saw not a blank bit of sky, despite the fact the projector wants to blank things out, apparently, whenever I get to the interesting bit. Despite the projector's protestations, here is what Hubble actually saw when it looked at a patch of sky. It is not empty. It is absolutely chocker full, and those aren't stars. There are 1 or 2 stars in this field of view. There's a star, and there might be a third one there. Everything else is a galaxy. These are all objects outside our own galaxy. So our own galaxy contains many billions of stars, but these are star systems in their own right. Each of these is probably as big as our own Milky Way. And Hubble has shown that the universe is absolutely full of these galaxies. We sort of thought maybe they were, but until Hubble actually looked and took this very long exposure, the so-called Hubble Deep Field, we weren't absolutely sure. And you have to bear in mind that the field of view of these large telescopes is not enormous. If you've got a phone with a camera in it, it might have a very large field of view in order to get you and 26 of your mates in your selfie. But these telescopes have very small fields of view. If you think about how big the moon is in the sky, you can easily cover the moon with just your little fingernail if you hold it up at arm's length. But the field of view of the Hubble Space Telescope is just that little red rectangle there. It's a tiny patch of sky. So when we see thousands upon thousands of galaxies, and we remember that all of those are in a tiny patch of sky which is much smaller than the size of the moon, it's barely the size of a grain of rice held at arm's length, we realize that if that's the number of galaxies we see in a tiny patch of sky, there must be a huge number in the entire observable universe. It's been calculated that it's probably not in the billions, it's probably trillions of galaxies. 1 or 2 trillion galaxies is the best estimate we have currently of the number of galaxies that are out there. The ones that are quite close, the Hubble Space Telescope can see in exquisite detail. So if we want to know how galaxies behave, how do the stars in our own galaxy behave, and looking at our neighboring galaxies, we can see an enormous amount of detail if we look at the galaxies that are relatively close to us, not ones that are billions of light years away. This is a so-called barred spiral galaxy, beautiful, huge spiral arms coming from what appears to be a bar running down the middle of the galaxy. People are looking at images like this, trying to understand how did that galaxy come to be? How did it end up shaped the way it did? Our galaxy probably doesn't look like that. Why is that? Why does our galaxy look different to this one? We notice that some galaxies are not entirely in isolation. Some galaxies appear to be interacting with neighboring galaxies. Perhaps you can figure out why this pair is called the rose galaxies. This galaxy was probably a normal spiral galaxy, but it got a little bit too close to this one. And gravity is indiscriminate. It'll pull on anything in the neighborhood. So the stars in this galaxy are getting pulled on by the stars in this galaxy and vice versa. So they distort each other. They interact. We think this is an important part of galaxy evolution. We think the universe ended up the way it did because galaxies collide with each other. It's not as cataclysmic as it sounds. When 2 galaxies collide with each other, it's not the end of the life of the galaxy. It's a bit more like a wildfire, which can actually promote new growth afterwards. When 2 galaxies collide with each other, there's a whole riot, shown in pink here, of new star formation. It's the interaction, it's the violence of 2 galaxies colliding that starts a whole new process of star formation. So sometimes galaxy collisions are actually a rebirth of the galaxy, not the end of life by any means. It's an important part of how the universe evolves. If we look at what's going on inside our own galaxy, rather than look beyond our galaxy at other galaxies, we see, for instance, the end of life, sometimes the beginning of life, of stars. This is a star that ended its life quite a few thousand years ago. That little dot in the middle is what's left. It's the core of a star that's ended its life, and the outer part of the star was shrugged off thousands of years ago and is now forming this beautiful colored blue, yellow, red nebula that surrounds this central star. This is what's going to happen to our sun eventually. Not just yet, don't panic. It'll be quite a while yet. But when the fuel in our sun eventually runs out, it'll be changing. It'll be changing in various ways. We try and understand how stars evolve based on our understanding of the physics of what's going on inside a star and how gravity is trying to crush the star and the nuclear reactions inside a star are pushing outwards. When the fuel runs out, that balance is disturbed and the outer part of the star is shrugged off to produce a nebula like this, and the hot core of the star is left behind. So this, in a sense, is a picture of what our sun will look like, perhaps in a few billion years. If a star is massive enough, it ends its life far more violently in a supernova, or if you prefer, a supernova explosion. It's not an explosion as such, but a supernova is the end of life of a massive star, which can effectively expel material. Most of the material of the star gets expelled into the interstellar medium, into the space between the stars. And this is the Crab Nebula, a popular item to look for amateurs, but here again imaged with the Hubble Space Telescope, a relatively small field of view, so it had to effectively make a mosaic by taking lots of images and stitching them all together to make this image of the Crab Nebula. Again, an iconic picture taken from the Hubble Space Telescope. It was taken on multiple anniversaries. Every once in a while it got upgraded with new cameras. Remember the good old days when the space shuttle existed? Astronauts would go up on the space shuttle and swap out the cameras with the latest technology of cameras. So they changed every few years, as it were. And this is one of the last images it took of the so-called pillars of creation. We think this represents star birth rather than star death. Somewhere inside these huge clouds, stars are being born. But it's difficult to see because clearly those gas clouds are so dense, it's difficult to see what's going on. We can infer what's going on by saying the radiation from these stars is sculpting these pillars, and we think we're calling them pillars of creation because we think stars are being created inside these pillars. But wouldn't it be nice to be able to see inside? That's one of the limitations of visible light, is it's not very good at seeing inside very dusty regions like this region here. Also, when stars are born, we think they are probably born with planets, and planetary solar systems will develop. But early planetary systems are, again, so dusty, it's difficult with visible light to see inside. What we really need to do is to use a telescope that looks in a different wavelength of light, a different part of the electromagnetic spectrum, and then we might be able to see these sorts of details. And that's precisely why they decided to launch the James Webb Space Telescope. It took many years to design, many years to build, but eventually they said this is what we want because this will work in the infrared part of the spectrum rather than the visible part, and it will be able to see inside these very dusty regions. We'll be able to see planets forming around stars. And a second advantage of going to an infrared telescope is because the universe is expanding and the more distant objects that you look at, light has had a long time to go from that object to us because we are looking at very distant objects. Light has to travel a great distance. Light can only travel at a finite speed. So we're in effect looking into the past. So with infrared, because of the expansion of the universe, the light is getting stretched out, and what used to be visible light is now being stretched out to longer wavelengths. That's the infrared part of the spectrum. So a telescope that works in the infrared is great for looking for planets, but it's also great for looking at very distant parts of the universe that have had their light stretched considerably. So that's why they designed the James Webb. This is an idea of the scale. There's the Hubble primary mirror, a little over 2 meters in diameter, and there by comparison is the 6 or 7 meter diameter James Webb, which you can see is made of hexagons. Now, hexagons weren't just an aesthetic choice because they look really cool when you make a mirror out of them. It was chosen because basically an origami requirement is that the James Webb had to be put on top of a rocket, and no rocket was big enough to have a mirror 6.5 meters in diameter. So they designed it to be that size, but they had to fold it in order to put it into a small cylinder to put it on top of a rocket and then launch it on Christmas Day 2021 to do its stuff. So basically they had to design it as hexagonal segments, and then they hoped that having wrapped it all up, they hoped that once it got to where it was finally going to be working, it would unfold itself and then do its stuff. So there's an awful lot of things that could have gone wrong with the James Webb Space Telescope. It's an enormously technical problem to actually fold something up like that and then have it unfold itself by effectively remote control a considerable distance away. The Hubble Space Telescope is in orbit around the Earth, but the James Webb Space Telescope was sent to a different place altogether. It was sent to a parking spot called a Lagrange point. We're not going to go into the details. You'd be glad to know. It's rather mathematical. But there are certain points in the solar system that can act as parking spots for spacecraft. So-called Lagrange point 2, or L2 for short, is one of those points. It's effectively a point sitting above the midnight of Earth. So this side of Earth on the left is facing the sun, so that's where noon is, and the point immediately opposite that is the midnight point, and L2 effectively floats 1 million miles above the midnight point on Earth. And that's where the James Webb is slowly sitting, orbiting the L2 point 1 million miles above the Earth. It's 1 million miles away because the James Webb is looking at infrared light. It's effectively looking at heat. And the last thing you want is a hot object like the Earth interfering with your measurements. So it's got this sun shield. It doesn't actually operate in this configuration. It turns itself so the sun shield is shielding the moon and the Earth and the sun from the delicate instrumentation that is looking for the infrared light from very distant objects. Again, Slightly technical, so go to sleep now. I'll wake you up in just a minute. But if we think of the timeline, we believe the universe was created about 14 billion years ago in the Big Bang. So here's a timeline. That's where we are now, about 14 billion years later. And as I say, we think the universe, we have observational evidence that the universe is expanding. And the more distant objects we see, the light has taken longer to reach us, so we're effectively looking back in time at the more distant objects. How far back in time can we actually see? Compared to where we are now, can we look back halfway through the lifetime of the universe? Can we look back to the first 4, first 3, first 2 billion years? The big question we want to answer is, when were the first stars and galaxies made? We know there are shed loads of them now, there are trillions of them now, but when were the first stars and the first galaxies made? How far back in time do we have to go? We think all the action, all of the really interesting stuff, happened in the first billion years or so. In other words, galaxies, we're not sure exactly how old our Milky Way is, but we think it's probably 10 billion years or so old. And all the interesting stuff happened here. If I expand that scale a bit, so there's the first 500 million years or so, the first few 100 million years. How far back in time can we go to actually see the first stars and the first galaxies? Hubble tried that, and it got to about there. Hubble got to about the first 500 million years or so. And it's found that stars already existed. Galaxies already existed 500 million years after the Big Bang. So they were made before that. It's hoped that the James Webb, with a larger mirror and working in the infrared, will be able to look at more distant objects and go further and further back in time. We'll never get back to the Big Bang itself, but how far back can we go before we can say, yep, those are the first stars, those are the first galaxies that formed. Now we can get an idea of how they evolved since then. We're hoping that given time, the James Webb has only been up there for a couple of years or so, given time, the James Webb Space Telescope might be able to get back to that sort of time period there. The numbers in red, by the way, are just how much the light has been stretched since it left these particular objects. So a Z of 14 means the light that left the object has now been stretched 14-fold before it's finally arrived here on Earth or at the James Webb. Visible light has been stretched into the infrared part of the spectrum. So lots of images were released when James Webb eventually got to where it needed to be and everything was calibrated and everything was tested. Then they pointed it at a few objects and released various wonderful images of galaxies and nebulae, and this part of a nebula here which gave this wonderful coloring, bearing in mind that you have to, of course, use false coloring. We're talking about infrared, so you take images at different infrared wavelengths and then you make a color image out of what you end up with. It's no different from the way the Hubble Space Telescope works, but it's a little bit removed simply because, of course, we can't actually see the infrared ourselves. We rely on the detectors in the telescope to show us what's going on. But the pillars of creation, rather than having lots of stars shrouded by the pillars of creation, we can now start to see inside the pillars of creation. So again, this object was revisited by the James Webb Space Telescope, and now instead of seeing dozens of stars, we can see thousands of stars, because although the dust is still there, with infrared light, we can start to see inside and get a better idea of how these stars are being formed and how the stars are being born in this various rich part of this particular nebula where lots of hydrogen gas is collapsing to form these stars, which then sculpt these pillars. It also looks, the James Webb also looks a little closer to home, just because it can. And so it, for instance, took an image of Jupiter using the James Webb there on the right. Here's an equivalent picture with the Hubble Space Telescope. They're rather different sizes. Remember, the Hubble is 2 and a bit meters. The James Webb is about 6 meters. but they're operating at different wavelengths. So you end up with about the same detail. If you look at the smallest detail you can see in the Hubble, it's about the same as the smallest detail you can see in the James Webb. But clearly they are showing us very different things. This on the left is basically what Jupiter looks like in visible light. On the right, it's showing us, in a sense, heat. It's showing us that different parts of Jupiter are radiating strongly or not so strongly based on how much heat is being generated or absorbed or emitted in the various belts of Jupiter. We also notice this is not an artifact. There's a little bit of a tinge at the bottom and a tinge at the top. This is not an error. This is not an aberration of the optics of the telescope. This is telling us that Jupiter has aurora. It has northern lights and it has southern lights, just like you might have been lucky enough to see recently or a few months back. So again, we can get better understanding of the planets, not just by looking in visible light, but by looking in infrared light as well. James Webb also revisited the Crab Nebula that we saw before. Again, this is the result of a massive star that's come to the end of its life. It was observed to go bang in 1054. There are records, there are Chinese records going back to 1054 that said a bright new star appeared in the sky. And it turns out to be this that went bang at the time. If we compare the James Webb image with the Hubble image, if I can do this carefully backwards and forwards, there's the Hubble, there's the James Webb, there's the Hubble, there's the James Webb. Can you see a slight difference in the size of the... It's not just that we're imaging in different light and so seeing it slightly different. Because we're seeing it 20 years later, the original Hubble picture is now 20 years old. This thing happened 1,000 years ago. So 20 years is a non-trivial fraction of that 1,000 years. In other words, this particular explosion, this particular nebula that was generated by lots of material thrown out of this star, it is literally a little bit bigger. It's a few percent bigger simply because we've got 20 more years after the original explosion 1,000 years ago. So it is useful, it is complementary to use James Webb and Hubble images to see various objects. But this is one of the ways that James Webb really pays for itself. It's able to see stars in formation. So this rather beautiful image here, all of the stars have these characteristic 6-point spikes, which are just a characteristic of the way the James Webb works. But within that, we can see lots of stars forming. One large cloud of hydrogen is collapsing to produce a large number of individual stars. Our sun appears to be a solo star, a star on its own, but it was probably born with a whole load of siblings. It's just lost them because it's been drifting away for billions of years. But here we're seeing a whole set of stars being born at approximately the same time, and this is helping us understand how stars are born, how they're born in clusters, and what happens to those clusters in the very early life of those stars. And again, in visible light, it would be very difficult to see the sort of detail that we can see in all of the stars being born out of this particular cloud of dust. Again, a little bit scientific, a little bit technical, but one of the most amazing images that Hubble came up with, and it was released a little while ago, literally weeks or only a couple of months ago. There's a star here on the left, ignore that. There's a tiny little smudge inside that square, and if we blow it up, it's a less impressive big smudge. But that particular object, it has been decided by various experiments, in other words, looking at the spectrum and carefully analyzing it. That is the most distant galaxy that has ever been seen by mankind, basically. That we know from the way light has been stretched from the early universe. We now know that if we take this particular scale, remember that's 0 to now, and we've expanded that little bit there. So Hubble got us down to 550 or so million years after the Big Bang. That particular object is Z14. The light has been stretched by a factor of 14, which means we've now got back to 300 million years after the Big Bang. And already we see galaxies. Already stars have been around for ages. We even see evidence that there's lots of huge black holes back in the early universe. How did they form so quickly? This is what theorists are now dealing with. The evidence is that if we go back in time, we see stars and galaxies that existed much earlier than we would have expected. A lot of people assumed that after the Big Bang, it would have taken ages before stars started to form, and then planets started to form, and then, who knows, life started to form after that. But apparently, stars and galaxies were being formed much earlier than we can currently understand. And that is stretching the theorists in trying to understand what's going on. The observation is there. It's going to continue pushing back, maybe in another year or two. James Webb will see even more distant objects and will push that back to the first 200 million years. And again, we can ask the question, when did those first stars switch on? In addition to the space telescopes I've been talking about, the Hubble and the James Webb, there are a number of new ground-based telescopes that will be coming online fairly soon. This one is under construction and is nearly ready. It goes by the horrible title of the Large Synoptic Survey Telescope, which is a real mouthful. They really need to find a better name. The actual telescope itself has been renamed the Chamonix Telescope, but because the LSST was used so much as an acronym when the Large Synoptic Survey Telescope was being produced, they really dearly wanted to hang on to that acronym, even though the telescope has been renamed. They didn't want to have a new website. They've already got lsst.org. They don't want to have to change that. So they decided to reuse LSST. Now they're saying we're going to do a survey. We're going to do a legacy survey of space and time. What that means is this telescope, which is nearly ready, that's what it looks like at the moment. Again, difficult to get scale, but there's a little person standing next to it there. So this is this particular telescope is perhaps a little smaller than this lecture theatre, but not by much. The idea is this telescope, unlike the Hubble and the James Webb, won't look at a tiny, tiny, tiny patch of sky and hope that the rest of the sky looks the same. It's going to try and survey everything that's out there. Remember, that was the Hubble Space Telescope field of view, a tiny percentage of the field of view of the full moon. The field of view of this survey telescope, which I'll just call the LSST from now on, is a lot bigger than that red rectangle. It's so big I can't actually fit it on the slide. It's a circle that you can see the top of it there. How do you build a telescope that has a field of view that is enormous compared to the field of view of the Hubble or the James Webb Space Telescope? Well, you start with a big mirror. Yes, it looks like a Christmas cake, but that is a glass mirror, and you can see the scale from the people sitting around it. It looks a little bit like it's got hexagons in it. That's just the structure of the glass that gives it strength. So this is a piece of glass which is made to the right curvature to reflect light, and once it's finished, it's coated with metal to give it a nice reflective surface. So you start with a mirror that's 8 meters in diameter, but that doesn't give you necessarily a large chunk of sky. It collects an awful lot of light, fantastic, but how do you get a large chunk of sky? Well, that depends on the camera. Remember that if you're, well, I presume everybody has a phone that is switched off at the moment, and inside that phone there'll be a camera. And the camera, of course, is tiny. The camera in your phone is barely a few millimeters or so in size. It has to be, otherwise you wouldn't be able to carry your phone around. To give you a comparison, how big is the chip inside the Hubble Space Telescope that's produced all of the wonderful images that it's produced? The chip in this sort of thing might be a couple of millimeters or so in size. Basically small enough to swallow and you'd hardly notice it, basically. The chip in the Hubble Space Telescope at the same scale is 4 centimeters by 4 centimeters. So it's that size compared to a finger, or that size if I hold it up in real life. It's large, but not enormous. Okay, some of you might have cameras, digital SLR cameras or mirrorless cameras or bridge cameras. They might have chips inside them which are centimeter size. So it's not necessarily huge, but it is large enough for the Hubble to do its job. With a large focal length, 16 million pixels in a chip that size will give you the sort of wonderful images that we've been looking at up till now. How big is the detector inside this LSST that has to be large in order to get a large chunk of sky? Well, not surprisingly, it must have a CCD detector, a chip, bigger than 4 by 4 centimeters. Let's start with that 16 million pixel Hubble chip. Let's imagine taking that Hubble chip and adding another 8 of them to get a little package. Now let's take that package of 9 Hubble-type chips and add a few more. Let's add another 8, and then another 12. And then we'll need a few more bits and pieces just to make it work. The chip inside this telescope is that size, a decent coffee table size. That is a 1-to-1 mock-up of the size of the CCD. The pixels in this are, roughly speaking, the same distance apart as the pixels in your phone. But the pixels in the chip in your phone might only be millimeters in size. This is 0.6 meters or so on a side. So instead of generating an image with millions of pixels in the image, it generates an image with 3 billion pixels. And I can't possibly show you what that might look like. It's being built, it'll be ready soon, it might be taking first light next year, it might be starting its survey the year after. I can't possibly show you what it can do, but I can give you a flavor of what it can do by taking the entire chip and saying, in one exposure, what might it see? Let's just look at that tiny black square there and say, what would we see if we zoomed into that tiny, tiny, tiny part of the entire image? What you might see is thousands of stars and hundreds of galaxies in that one thing alone. That's just a simulation of what you might see if you just pointed at a random part of the sky. But the actual image it takes in a 15-second exposure, not 10 days, not 3 hours, not 1 hour, not half an hour, in a 15-second exposure, it would end up capturing that many stars and galaxies multiplied by whatever area we haven't looked at. The entire area there is 3,000 times more than the little sample we've just looked at. So thousands of stars and hundreds of galaxies would have to be multiplied up 3,000-fold, and that is what it will catch in a 15-second exposure. And this telescope is going to take 15-second exposures of the entire sky every 15 seconds, all night, every night, for 10 years. And it will map the entire sky over and over and over again. Not only will it map out what's there, it will keep returning to the same object every few days, and it will say, how is it changing? Has it changed color? Has it changed size? Has it changed brightness? Has it moved? Is it not a star? Is it an object in the solar system? So that's the idea of a survey telescope, not looking at anything in particular, but literally looking to find out what is out there by surveying the entire sky, or at least the entire sky from where this telescope is sited, which is in Chile on top of a mountain. The best skies, pretty much the best skies in the world there in the Atacama Desert. So it'll be looking to see what it can find by surveying the sky over and over and over again. When it finds something interesting, which it will do probably every night, it will probably find thousands of objects we didn't know in the solar system, thousands of comets and asteroids and lots of other objects. Because it will be covering essentially the entire sky, it will find thousands of new objects. It will find thousands of supernova, stars that have decided to explode. In the history of mankind, we've seen about 1,000 supernova go off. Various telescopes around the world looking at various galaxies have seen about 1,000 stars go supernova. When this is operating, it should get 2,000 supernova every night. And it will do that night after night after night for years. It will generate enormous amounts of data. Far too much data for PhD students to analyze. We're going to have to find very interesting ways of getting computers to triage the data to tell us where's the interesting stuff, because there's going to be so much of it, it'll be difficult to work out what's going on. But all of the interesting stuff, this star has moved, or at least this planet has moved, this object has moved, this star has changed brightness, that galaxy now has a supernova, there's a new comet over here, there's a new star over there, this star seems to have changed its color. Anything that looks interesting will then be relayed to other telescopes around the world, such as the Leviathans that are now being built. This is the European extremely large telescope. It's got a mirror 40 meters in diameter, again bigger than this lecture theatre. And again, there's people in the front there and a few people on the gantry, just to give you an idea of scale. So these telescopes are absolutely huge. They're based on the Earth, so we still have to look through the atmosphere, but the collecting power of the light is going to be enormous because of the size of these mirrors. So a survey telescope will be able to find the interesting stuff, and then either space telescopes or telescopes like this with large mirrors, if these objects are quite faint, will be able to collect the light, produce the images, take the spectra, try and work out what they're made of if you're looking at a very distant planet or a distant galaxy, try and work out what's going on by looking at the images and looking at the spectra by taking the light and breaking the light down into its component colors. Again, these sorts of telescopes are coming online. The European Extremely Large Telescope is being built and will take light perhaps 2027, so almost imminent. It's been under construction now for quite a few years. This is the European Extremely Large Telescope. The Americans are also working on a telescope of a similar size, but lo and behold, they're way behind. The Europeans are going to win. We're going to get there first. And I say we, this is nothing to do with the EU. This is a European effort of lots of countries, including the UK, that are contributing to telescopes like this. And if you're worried about the cost, I did a quick calculation before today. These telescopes are indeed expensive, but the cost is spread over lots of European countries. So if you work out, assuming you're taxpayers and not dodging your taxes, each of you in the audience has probably contributed to this telescope to the level of approximately 10 to 20 pence per year for the last 10 years. That doesn't sound like much, but if you add it up over millions of people throughout Europe, you get a telescope like that. So yes, science is expensive, but the question is, can you afford a few pence? That's the bottom line. So let's just return to this. Remember, that was our biggest telescope in the world, and we are then getting things like the European Extremely Large Telescope coming online in the not too distant future. Is that going to be 40 meters? That's what the Americans are working on, the 30-meter telescope. So even if they were to catch up, it would only be 30 meters, not 40 meters. So we still win. So is that the largest telescope we can ever conceive of? Well, it's the largest telescope we can afford at the moment, and it's rather difficult to think about how you could raise the funds to make anything larger. But people have said, well, why should we stop at 40 meters? That's fine for the next few decades, but let's think into the future. Is it possible to build a telescope the size of the red circle? Well, no reason why not. Technologically, we could probably do it. It would be ridiculously expensive, so we're not going to do it just yet. But people have said, yeah, we may as well at least think about these things. And if we want to think about everything we've learned from building a 40-meter telescope, we can think about making larger ones. We would end up with a telescope that could see more detail and see fainter objects. What on earth would we call this telescope? We've already used Very Large Telescope, VLT. And now we've shot our bolt because we've now used the Extremely Large Telescope. So what on earth would we... Some people have said, let's call it the Owl. Why would we call it the Owl? Is that because owls have large eyes? No, it's because it would be the Overwhelmingly Large Telescope. Which is fair enough. I think that's probably not a bad idea. So that's where we stand with telescopes. We need to have lots of different types of telescopes. We need survey telescopes which can look at incredibly faint detail but can still survey the entire sky in a matter of nights thanks to a huge mirror and a huge chip the size of a coffee table, which will allow this camera, which is about the size of a car, to actually image the sky over and over again, night after night after night, and basically find out what is out there. And then that will feed into space telescopes like the Hubble and the James Webb and whatever the next generation of space telescopes will be. And it will also feed into these large aperture telescopes such as the 30-meter telescope and the European Extremely Large Telescope to look in detail, because those telescopes don't have time to survey the whole sky. They will be told by the survey telescope, this is interesting, that's interesting, that's interesting, go look at those in more detail. So basically, it'll be the complementary characteristics of different types of telescope that will allow us, hopefully, survey telescopes, space telescopes, large aperture telescopes. They will enable us in decades to come to address the most interesting questions about the universe. And perhaps even more importantly, it'll tell us which questions we haven't thought to ask yet. Thank you all for listening.